I have written an article on Medium about bioinformatics Rust WebAssembly some time ago, and I wanted to share it here as well. To summarize it in a minute, it's about how Rust could be an excellent choice for a programming language when it comes to bioinformatics. My main points are that 1. In the field of bioinformatics, genomics, performance often matters, and Rust is ideal for memory-efficient, high-performing, multi-threading programming. The second point is that Rust can easily provide bindings to Python, and Python is an extremely popular programming language in science and bioinformatics. The third point, Rust can easily provide bindings for WebAssembly, which makes the library and applications run on the web without the need for a dedicated web server. And fourth, Rust is a modern programming language that is growing in popularity and is here to stay. So there is an opportunity to rewrite all libraries and applications that has been made in Perl or C or even all C++ like 2 decades ago. To start the explanation, I think it's useful to explain where I'm coming from since I'm not a bioinformatician. I mainly worked as a front-end engineer, and in front-end engineering, Rust has been growing in popularity for a long time now. And the main reason is performance, especially when it comes to development tools like TurboPack, Vite, Biome, Lightning CSS, etc. Rust is now the programming language used for tooling in the Node JavaScript ecosystem. Parsers and bundlers have been rebuilt from scratch, rewritten for performance in Rust. And that's where my introduction and interest in Rust is coming from. I have been introduced to bioinformatics a couple of years ago, and when I looked into it, I made a few observations that led me to believe Rust could be an excellent choice. So I decided to take this opportunity to try it myself and rewrite a bioinformatics library called Prodigal in Rust. This would be a good opportunity for me to learn the language practically. So that being said, let's look at the reasoning as to why this language could be ideal. First, Rust is extremely performant and has proven itself to be an excellent choice for building fast and memory-efficient libraries and applications. At its core, Rust gives you the low-level control normally associated with C and C++, combined with the safety and correctness guarantees of a modern language. This combination is very well suited for bioinformatics, where tools often process large number of sequences. Writing multi-threaded code in Rust is extremely straightforward because of libraries like Rayon, which makes parallelism easy to use. Instead of manually handling threads, locks, and shared state, Rayon allows you to parallelize a standard iterator by replacing a single method. Rust also provides access to SIMD intrinsics, which allow algorithms to take advantage of CPU vector instructions. Another point is the absence of a garbage collector. Since Rust doesn't rely on garbage collection, there is no unpredictable pauses during execution. The result is consistent and predictable performance. So now the result for my little rewrite. I benchmarked it against 2 other implementations. Prodigal, which is the original version that was written in C, and Pyrodigal, which is a Python binding that uses Sidon and SIMD operation for additional speed. And the third one, obviously, that is my Rust implementation that I called Orphos. The results were quite interesting. The Rust version was faster than the original C version in single-threaded mode. When multi-threading was enabled through Rayon for a single sequence, the performance continued to improve, although not a lot. One thing I want to clarify with this is that it's not meant to be a demonstration on how Rust is faster than other languages. It's more a demonstration than rewriting a tool in Rust with modern abstractions, clearer data structures, easier parallelism, and safer memory handling can naturally lead to equal or better performance. As mentioned in the previous section, a Python binding library for Prodigal already exists. It's called Pyrodigal. And the reason Pyrodigal was created is simple. Python is one of the most widely used languages in science and bioinformatics, so being able to access a genomic tool directly from Python is extremely valuable. Many scientists want to work inside Jupyter notebooks, combine results with NumPy or pandas, or run parts of their pipeline in Python scripts. But most classic bioinformatic tools do not provide any native Python interface. They were designed to run as standalone executables, and the only way to integrate them into a pipeline is by calling their command line interface. This creates a style of interoperability that depends on chaining together multiple tools by running them as subprocesses. Pipelines often become a long sequence of CLI calls written in Bash or Perl, with intermediate files passed from one tool to the next. This approach works, but it's fragile and slow. It forces users to deal with temporary files, text parsing, inconsistent output format, and a complete lack of type safety. The integration happens outside the language instead of through a very simple, well-defined API. Like I said at the beginning, my background is in front-end engineering, where this type of fragmentation almost never happens. In that world, everything must eventually run in JavaScript for the web, and this creates strong pressure to provide clean bindings and easy interoperability. Even when Node.js introduced server-side execution and developers started writing native extension in C or C++, the final interface almost always exposed a clean JavaScript API. The ecosystem expects tools to work together programmatically, not only through command line calls. So Rust brings the same mindset to bioinformatics. With the PyO3 libraries, it becomes very easy to expose Rust functions, struct, and modules directly to Python. You write Rust code as usual, add a few annotations, and PyO3 generates a Python module that feels completely natural for Python users. This means a single Rust codebase can provide a command line interface, a Python package, without forcing you to maintain separate implementations. In the case of Orphos, my Rust implementation, adding Python bindings required only minimal changes to the code. Within a short amount of time, it was possible to publish a pip installable package that behaved just like Pyrodigal but rely entirely on the Rust implementation. This improves usability, make the tool accessible to a much wider audience, and eliminate the need to create Cython-based bindings. CRISPR-Cas5 was one of the first tools that introduced me to bioinformatics. What immediately stood out was how convenient their online version was. Having a web interface that works out of the box is a huge advantage. You upload a file, click a button, and receive the results. There is no need to set up dependency or troubleshoot your environment. Once you look behind the scene, you start to understand why many researchers rely on these web servers. As explained before, a large number of classic bioinformatic tools are actually collection of Perl script that calls another command line tools, each of which may be written in different language with its own installation process. The tool might require a specific version of Perl modules, C binaries, Python scripts. Each dependency becomes a potential point of failure when installing the software locally. This makes installing those tools a nightmare. The most common way to solve this issue is containerized system like Docker. If a suitable container doesn't exist, you will end up creating your own, which is not ideal. This is why bioinformatic tools hosted as web servers are useful. But hosting a web server requires maintenance, funding, and continuous updates. These services can disappear without warning. While I was looking into Prodigal, for example, I found discussion in their Google group mentioning that the official web servers were down. Once the funding or support for a web service ends, the entire tool becomes inaccessible unless users install it locally, which brings back the original problem. In a traditional setup, the online version of a tool receives a job request, send it to a server, wait for the computation to finish, and then return the result. This model requires a running backend and all the infrastructure that goes with it. Rust and WebAssembly offer a completely different approach. With WebAssembly, the program can run directly in the user's browser. The computation does not happen on a remote server. It happens locally on a user machine. The software requires no installation and there is no backend to maintain. A web app can simply load a WebAssembly module and run the analysis immediately. Downside of it is that the speed of execution depends on your own machine and not the external server. Even without a web interface, Rust also makes local installation simple. A Rust project can be compiled into a single binary for each platform and operating system, which avoids the dependency issue that many older academic tools suffer from. Adding a WebAssembly version of a Rust library is also surprisingly simple. The tooling is mature and deployment can be automated through GitHub. In my case, I created an online version of Orphos that runs entirely on the client side. Rewriting Prodigal in Rust was an excellent way for me to get hands-on experience with the language, but the process also revealed something deeper about software engineering in bioinformatics. A huge portion of the foundational tools were written decades ago, in languages that were powerful at the time but are quite difficult to maintain today. Reading the original C code for Prodigal or the Perl code for CRISPR-Cas5 was a challenge. Not because everything was written poorly, but because languages like C naturally encourages a very low-level style. Memory management is manual, data structures are often implicit, and the flow of logic can be spread across multiple headers files and macros. Rust approaches things differently. Its design encourages you to model your domain clearly with structs and enums that express the actual biological concept you're working with. Parsing logic, scoring system, gene models, codon tables, they all become explicit types with well-defined method. Instead of mentally tracking mutable pointers or shared buffers, the compiler forces you to state your intention clearly through ownership on borrowing. You spend far less time worrying about how memory is handled and far more time designing the right abstractions. Multi-threading, which is unsafe and error-prone in C, becomes almost effortless in Rust, with tools like Rayon allow you to parallelize CPU-bound loops with a single method. Another advantage is documentation. Rust gives you a complete documentation website for free the moment you publish a crate. Every struct, method, example, and module is automatically rendered into a clean API docs, which is something that all bioinformatic tools rarely provide out of the box. This makes Rust library much more approachable for new contributors or for scientists who want to understand what the tool is doing under the hood. And finally, Rust isn't going anywhere. The language continues to grow rapidly and is backed by major organizations like Amazon, Google, Microsoft. Many high-performance systems, from cloud infrastructure to browser engines, are already adopting Rust as a safer, more modern alternative to C and C++. So the investment in the ecosystem means that the tools, compilers, and libraries we rely on will only get better. That's it for me. I left links to the repository down in the description.